The second example, this stochastic process is a continuous time discrete state stochastic process. So here let n of t, where t varies from 0 to infinity, be a Poisson process with the intensity lambda or parameter lambda, and the f of t is its natural filtration. The natural filtration means it has the information till time t, and each random variable n of t for fixed t is ft measurable. That is the meaning of natural filtration. We know that for fixed t, n of t is a Poisson distributed random variable with the parameter lambda. Therefore, the mean of n of t, that is same as the parameter lambda. So the first condition is satisfied. The second condition, for fixed t, n of t has to be ft measurable. Since it is a natural filtration, the n of t is a ft measurable. The third condition we are going to verify. The conditional expectation of n of t given f of s, where f of s is the filtration at time s or the information till s. Obviously here s is less than t. So to find out this conditional expectation, what we do, we add and subtract n of s with the n of t. So instead of a conditional expectation of n of t given f of s, we subtract n of s and add n of s. Expectation is a linear operator. Therefore, you can split these three terms into two different expectations, conditional expectation. Therefore, the first one you can keep n of t minus n of s. The second one you can keep it separately, n of s. Hence, you have conditional expectation of n of t minus n of s given the filtration f of s plus conditional expectation of n of s given f of s. The first term, this conditional expectation is nothing but, you know the information till time s, and we are asking the conditional expectation of n of t minus n of s given f of s. That means that this t minus s and s, this is a non-overlapping intervals. S is a point, t minus s is the non-overlapping intervals. So this is the random variable corresponding to the non-overlapping interval with respect to s. Therefore, you know the property of Poisson process. For s less than t, n of t minus n of s is nothing but the increments. The increments are stationary and independent. Therefore, the n of t minus n of s is independent of f of s. If it is independent, the conditional expectation is nothing but expectation of n of t minus n of s. You know the Poisson process properties. Since n of t is a Poisson process, n of t minus n of s for fixed t and s, this is a Poisson distributed random variable with the mean lambda times t minus s. Therefore, this conditional expectation will be lambda times t minus s based on the n of t minus n of s is independent of f of s, and for fixed s and t, n of t minus n of s is a Poisson distributed random variable with the mean lambda times t minus s. Whereas the second term, conditional expectation of n of s given f of s, that means for information till time s, what is the expectation of n of s at the same time s. So since you know the information till or up to the time s, n of s is constant. N of s is a constant. Therefore, expectation of constant is a constant. Therefore, it is n of s. It's not a lambda times s, because the the information till time s. Once you know the information till time s, that means you know the value of n of s also. Once you know the value of n of s, therefore n of s is no more a random variable. So it's a constant. So expectation of a constant is a constant, so it is n of s. Hence, conditional expectation of n of t given f of s is same as, you can take a lambda t in this side. So conditional expectation of n of t minus lambda t given f of s is same as n of s minus lambda times s. If you see, this is a expectation of n of t minus lambda s given f of s, that is same expression. Therefore, as such, expectation of n of t given f of s is not n of s. It has the some positive value. T minus s is always greater than 0. Therefore, lambda times Lt minus s will be greater than 0. Therefore, this conditional expectation is always greater than or equal to n of s. Hence, n of t is not a martingale, whereas if you treat n of t minus lambda t as a stochastic process over the t ranges from 0 to infinity, then this stochastic process is a martingale. The n of t is not satisfying is same as n of s. The conditional expectation is not equal to n of s, but it is greater than or equal to n of s. Therefore, n of t is not a martingale, whereas if you make another stochastic process, that is nothing but n of t minus lambda times t, or t greater than or equal to 0, then this stochastic process satisfies the third condition and also satisfies the other two conditions. Therefore, the n of t minus lambda t is a martingale. Third example, this is related to the application of finance. Consider the binomial tree model. Let Sn be a stochastic process and Fn be its natural filtration. Define the probability of Sn plus 1 given u times Sn given Fn, that is same as, that is P, and the probability of Sn plus 1 is equal to d times Sn given Fn is equal to 1 minus P, where u and d are the next value of Sn with the probability P and Q respectively. Therefore, suppose the previous the nth value was Sn, then the next value will be, it is decremented with d, therefore d times Sn, or it would have been incremented with u, therefore u times Sn will be the Sn plus 1th value. Therefore, this stochastic process is called the binomial tree model. Now I am considering the discounted stochastic process, that is nothing but e power minus r times, basically e power rt s of t. Since it is a discrete time stochastic process, the first s1 is multiplied by e power minus r, whereas the second random variable s2 is multiplied by e power minus 2 times r, and so on. Therefore, the nth random variable Sn will be e power minus n times r, where here r is the riskless interest rate. So, whenever you multiply the e power minus r times t, the corresponding stochastic process is called the discounted stochastic process. The discounted stochastic process is a martingale if only if the right hand side is equal to e power minus n times r times s, because here it is a conditional expectation of e power minus n plus 1 times or s n plus 1 given fn. If this quantity is same as e power minus n times r multiplied by sn, then this discounted stochastic process will be a Martingale, or it has the Martingale property. So this is the case only if the p value takes e power r times minus d and divided by u minus d. If the p is the probability of incremented by u, if the p is equal to e power r minus d divided by u minus d, then the discounted stochastic process is a Martingale. So that is possible because since p lies between 0 to 1, since whenever the r is the riskless interest rate, e power r is also lies between d to u. Therefore, the u minus d and e power r minus d, this values is going to be lies between 0 to 1. So therefore, with the proper value of r, d and u, the p can be, if the p is of this form, then the discounted stochastic process is a Martingale.